Great. All right, well, thanks for the introduction, Lynn Kay. My name's Jeff Watson. I'm the staff, one of two staff hydrogeologists at Barton Springs Edwards Aquifer Conservation District. A little bit of background, I've been a geologist for about 7 or 8 years now. I started with Trinity. I went to grad school at UT Austin and also did my undergrad there. And I'm a native Texan, native Austinite, so yeah, from around here. I spent a lot of time in Hays County growing up. Today I'm going to be talking about a project that we've been working hard on for the last couple of years, our new in-house Trinity numerical model. It segues nicely from what Director Torres Verdin was talking about because quantification of groundwater is really one of the main goals of this model. So a mandatory disclaimer at the front end. This model is still undergoing peer review right now, so any of the results you see here today should be considered preliminary, subject to us publishing our final report on the model. And just a general quote about models is that all models are wrong and some are useful. Particularly with this model and any model on the Trinity, we're going to be dealing with a lot of uncertainty, which is another thing that Director Torres was pointing out. Just because we don't know, the Trinity is a much less studied aquifer than other aquifers like the Edwards Aquifer. So we have a dearth of data. There's a lot of uncertainty around things like recharge and different aquifer parameters and different local conditions. So in building this model, we've had to make a lot of assumptions that may or may not be true, but sort of quantifying the uncertainty associated with those assumptions accurately, we can still produce a model that can be used to guide and make overall predictions on aquifer behavior under different scenarios. So a couple of different types of models. So conceptual model is basically it's kind of how we think about a groundwater system, how we think a groundwater system works. So this takes all of the data that we have on an aquifer, whether it be water level data from monitor wells, aquifer testing data, geochemistry data. We compile all of that data and put our heads together and come up with our best idea of sort of how recharge enters the aquifer, how water discharges from the aquifer. There's been a lot of great geologists that have been working to build a conceptual model for the Trinity. Doug is here. He's been a big part of that work over the years. Other geologists like Marcus Gary and Brian Hunt, Brian Smith have put a lot of work in improving our understanding of the Trinity and how it works. Another type of model is analytical models. So this is basically where we look at the localized impact from a pumping test and we use equations to fit drawdown numbers to graphs to come up with localized aquifer parameters. So this is basically what we do anytime you have a permit application and they conduct an aquifer test. They're required to collect data. They pump the aquifer. The aquifer has a cone of depression associated with that pumping, and then we can fit equations and have analytic solutions to that data to come up with our understanding of the localized condition of the aquifer. This type of model is very powerful locally and at predicting local impacts, but it breaks down as you go to a larger, more regional scale because of the inherent assumptions associated with it. So that segues us to numerical models. Numerical models are essentially where we create a usually three-dimensional computer simulation of a groundwater system. We've actually discretized the aquifer into specific cells and sometimes with multiple layers. The aquifer I'm talking about, or the model I'm talking about today, has 3 layers in it and about 250,000 active cells. And then we apply specific aquifer parameters to each one of those cells based on our best understanding of the conceptual model and the way that the aquifer works and the available data. And these models are these are the kind of models that we need to be more quantitative on a regional scale to make these larger scale decisions. And it's also important to note that these all kind of interact with each other, right? So the aquifer parameters are usually coming from analytical models. These get put into our conceptual model and our numerical models. And then likewise, there's also all of our conceptual understanding of the aquifer goes into the numerical models. And vice versa, we can use the numerical models to test hypotheses about the conceptual models and ideas about how the aquifer might work hydraulically. So that's one of the purposes of our model. I won't be talking about that as much tonight, but that is one of the uses for the model. Other ongoing numerical modeling efforts, so I'm talking about our in-house model today, but the Water Development Board is also working on the Hill Country Trinity GAM, the updated model, which I think they're calling the Southern Trinity GAM model now. We don't know when that's going to be finished. I talked to one of the Development Board staff last week, and they estimated maybe sometime in 2024. There's also the BROT model, the Blanco River Aquifer Assessment Tool. This is underway. It's being done by a modeler at Southwest Research Institute right now, and that's expected to be finished in 2023. It's a very high-level, complex model that's trying to model the groundwater and surface water interactions within the Blanco River and the Onion Creek catchment. All right, so here's our model domain. So the area that our model covers here is in red. So this is where we have active model cells within the model. Now, basically our main area of investigation is kind of here in the middle in central and western Hays County. So you can see this purple line is the district boundaries between Barton Springs District and Hays Trinity. So that's our primary area of investigation, but whenever we build models, we want to extend the boundaries of the model away from our primary area of investigation so that the boundary conditions of the model aren't impacting our area of interest, the simulations in our area of interest. A couple other key things to point out here. So geologically, our model only covers the Middle Trinity Aquifer, which is stratigraphically composed of the Lower Glen Rose, the Hensel, and the Cow Creek. The Middle Trinity is the most prolific aquifer in this area, also the one with the most wells drilled in it, and the aquifer where we have the most data. So this is really the only aquifer at this point where we have enough data to adequately model the system. But it's also the most important aquifer, so there's value in creating that model. On the next slide, we're going to look at a cross-section, schematic cross-section of our conceptual model, and I'll go through a little bit about how we think the aquifer works. So again, this is that first model that we were talking about, the conceptual model. So essentially, what we have here is in the western portion of Hays County, which is where we have Hays Trinity. The Middle Trinity units they're either exposed on the surface in the Blanco Basin, or they've got a thin veneer of Upper Glen Rose limestone on top of them, so they're less deeply buried. We think that almost all of the recharge in the area is coming in this upgradient portion. We have complex groundwater surface water interactions within Onion Creek and the Blanco River Basin. So where we have direct recharge from surface water streams as well as important artesian springs that I'll be talking about shortly. They're discharging into that basin. This delineates a very simple model of the Balcones fault zone. So the Balcones fault zone drops all of these geologic units down hundreds of feet, and then on the down gradient side of this fault zone you have the Middle Trinity being more deeply buried. We think that most of the recharge to this area of the fault zone is coming from up gradient from Hays Trinity. So essentially what we're talking about is one aquifer that's being managed by two different groundwater districts, but they're integrally linked. Another important thing to point out here is the wells. So any model is one of the important outputs is going to be wells, which is an outflow from the model domain, and there's wells developed in both of these districts. All right, so this is a very oversimplified explanation of how the model works, but essentially all the model does cell by cell is calculate inflows versus outflows. So Isaac Newton gets really upset if you create or destroy water. You have to have water be consistent within the model domain. So any water that comes in has to go out somewhere else, and vice versa. So there are more water balance items in this, but these are the three most important ones that I'll be talking about today. So we've got recharge, which is our inflow, and then our outflows are pumping and spring flow.
Jeff, can I ask a question?
Sure.
Where would storage fit into that equation? In the equal sign?
It would be in the middle of the equal sign.
Okay.
So you can have storage go up, you can have storage go down, and the way the model works is it conceptualizes that as like almost a separate water budget item.
Thank you.
But I didn't want to get too in the weeds. All right, so let's take a look at recharge. So based on our conceptual model, we think most of the recharge is coming into the Trinity through Onion Creek and the Blanco River basins. So that's our primary component of recharge. We've also got another component of recharge coming in laterally on a regional basis from Blanco and Gillespie counties. And then we've also got what we call diffuse infiltration. So in these sort of upland areas where the upper Glen Rose is outcropping, there's probably some level of slow infiltration coming in through those units in the other portions of the model domain. But we think that this component of recharge is much, much smaller than the other ones. So that for the purposes of modeling, this is essentially where we're allowing water to enter the model domain. All right, so spring flow is the largest outflow water budget item. The springs that we have explicitly modeled in our model are Jacob's Well Spring and Pleasant Valley Spring, which are the two largest springs in the area. Most of you are familiar with Jacob's Well Spring, which provides most of the flow to Cypress Creek. We've also got Pleasant Valley Spring, which less people are familiar with, but it's actually volumetrically larger. It has more flow than Jacob's Well Spring. It's discharging into the Blanco River a little bit upstream of the Fisher Store Bridge. And the Pleasant Valley Spring is basically the headwaters to the Blanco during times of drought. So it's a very important spring. And both of these are artesian springs that discharge directly from the Middle Trinity Aquifer. So we can include them in our water budget calculations. So where does all this spring flow go? Well, so we've got our two springs here. This is Cypress Creek. We've also got the Blanco River. All of that flow makes its way downstream, and you see these little red reaches along the Blanco River and Onion Creek. This is actually the Edwards recharge zone here. So in a sense, you can think of these springs as being an indirect connection between the Trinity Aquifer and the Edwards Aquifer. So a big part of our mandate at the Barton Springs District is protecting Barton Springs. And based on dye tracing studies we've done from these losing reaches, we've traced the flow from the Blanco to both Barton Springs and San Marcos Springs. So you can see that this water is important to us.
Is San Marcos Springs what used to be Aquarina?
Yes.
Okay.
And it's very interesting that during times of drought, we think there's sort of a groundwater divide. So during times of drought, more of it goes up to Barton Springs. Wetter times, more of it likely goes down to San Marcos Springs. And studies have shown that during times of extreme drought, the Blanco is basically the main water source providing recharge to the Barton Springs segment of the Edwards. All right, so pumping is our second major outflow water budget item. Map here, these are just a quick map of all the submitted drillers reports within Hays County and Blanco and Travis County. You can see all of the blacks are exempt wells and the bigger greens are permitted non-exempt wells. Hays Trinity has significantly more pumping than Barton Springs District, and that's likely because the Trinity is the only aquifer that you guys have. In Barton Springs District, we also have the Edwards Aquifer, and then there's also various surface water sources available. So within Hays Trinity, there's more pressure on the Trinity than within our district. You can also see a bigger percentage of the overall pumping is through exempt pumping, which are the orange guys here. All right, so jumping into model calibration. So after we have the model built out and all of our cells created, all of our parameters applied, then we go about calibrating the model to the real-time data. And here's some examples of that. So you can see here in red, these are our actual monitoring well data. And then in blue, this is the model simulating water levels over that data. One of the big tasks for any model is trying to get your simulated data to line up with the measured data. And in this particular model, that's a very challenging task because we're talking about a really big area that has various different regions of the aquifer that behave differently. We also calibrate to spring flow. So you can see here, Jacob's Well Spring, again in the red we've got our observed spring flow data, and in the blue our simulated data, and then for Pleasant Valley Spring as well.
So, can I ask a question?
Sure.
How would you rate that calibration versus observation?
I think, so for Jacob's Well, I think it's very good. Yeah.
So
For
all those observed measurements that go way up there, and all simulated measurements that are way down there, you think that's good calibration?
It all depends on kind of what areas of calibration you care about. So for us, we're focused on more the low flows than the high flows. And due to the sort of mechanics of the software that we're using, matching the high flows is a lot more complex than matching the low flows. So I think for the purposes of what we want to get from the model, which is sort of an overall matching of water budgets during low flow, I think it is a pretty good calibration.
Okay, so maybe that whole low flow objective should be in the very title of the deal, so that where we're looking at the presentation as, okay, this is the model we built, but really it's not built to simulate actual conditions, the high conditions, just the low conditions. So should that not be kind of laid out in advance?
Maybe.
Because if there's not a lot of groundwater modelers in here, they
Sure.
might not realize that.
Yeah, well, so I just wrote a 130-page report on this model. It's very complicated, and knowing which information to include and not include in a public-facing presentation, I think is...
Well, that would be a big
It's
one.
difficult.
That would be a big one. What is the actual objective of the model? That would be a big thing to include in the presentation.
Well, I kind of talked about that at the beginning, though, right? We're quantifying water budgets.
Low
You
flow
didn't
water.
say it. If you go back to the prior slide, that looks even worse, I think.
Thank you. I didn't want to sit there and tack, but I knew we'd get to calibration at some point. I have
Yeah.
4 years experience of drilling wells, installing wells in the Trinity, and pump testing wells and analyzing wells. And calibration matters.
I totally agree. And if you're interested, when we publish the report, there's a whole section on calibration, and we can talk about the decisions. So Doug is on it, the modeler from Southwest Research Institute. We've got Bill Hutchinson, Texas Water Development Board. I mean, we've got a good mix of professional modelers and hydrogeologists that understand the system.
I'd love to do an independent, third-party, conflict of interest-free peer review.
Well, why don't we chat
Okay.
after, and I'll go on with the presentation. We
Okay,
can
fair enough.
exchange contact info.
We just had a point.
All right, so once we have our model calibrated, then we can build out forecast models where we actually simulate different scenarios and how the aquifer might change based on those different scenarios. So the first thing we need to do is we build a baseline model. We try to make that approximate baseline conditions over a specific time frame. We have two baselines. We have a 50-year baseline that tries to approximate, essentially, if we take 2020 pumping and keep that steady for 50 years. And then we also take our recharge data set, which is a 13-year data set, and we cycle that over a 50-year. And then we also have a separate model, or a separate baseline model that is the drought of record model, which is it's a 10-year model, and we take rainfall data from 1947 to 1957. During the drought of record, it's actual rainfall data that we've used to create that recharge data set. and then we can overlap that with various pumping scenarios. And essentially what we do is we run two different models. We take our baseline model, and then we change something from the baseline model, and then we compare the two models. And that allows us to reduce the overall uncertainty in the model, because sort of all of the uncertainty, or much of the uncertainty is canceled out because both of the models have the same amount of uncertainty. We've only changed one factor in the model. In this case, it's either pumping or recharge. So what we're going to be looking at in the following slides is called residuals. So that's the difference between the baseline and whatever model scenario we're looking at. All right, so baseline model, I've already talked about this a little bit, but it's a 13-year recharge cycle. And then we basically take the 12-month pumping cycle and then cycle that through the entire 50 years. And then I'm going to show you what we're calling scenario C, which is our regional demand and pumping model. So it's our question here is what happens if our regional expectations for water demand are applied uniformly to pumping. What would be stimulated to change within the aquifer in terms of water levels and spring flow? So here's a look at the 2021 State Regional Water Plan. So we take our 2020 estimated future demand, and then we compare it, or 2070 and compare it to 2020. And the state's estimating that there's going to be 2.6 times as much water demand in 2070 than 2020. So we take that and we apply it to our model domain. So here you can see two different polygons that we've applied that additional water to. We ramp up that demand over the 50 years, so it starts small and then it reaches that 2.6x in year 50. And then we run the model forward and when we compare the difference between them. So here's that residual map. So again, this is not drawdown, this is just the difference between two models. This is us trying to isolate the potential impact of that additional pumping. That's the only thing different from the baseline that we're looking at. And this is a contour map that's representing those simulated difference in water levels. So we've got, within Barton Springs District, we've got a mean residual of 40 feet and a maximum residual of 91 feet. That's this kind of a red target that you're seeing here. And then it's about 15 feet and 92 feet in Trinity. So the way to think of this as this is what the model is predicting is the change in water level just from that increase in pumping, right? This doesn't include the variability of drought. That's all kind of accounted for. All right, moving on to spring flow. So what you can see here on the top is our baseline model simulated spring flow. And what you can see here on the bottom is our scenario, it should say scenario C actually, but yeah, so this is our simulated scenario C spring flow. And the difference between them is what we're interested in, right? This dotted line is our residual. So that's what the model is predicting is the difference in flow between the two models. And you can see we're kind of starting the same up here, right? Because remember that our demand growth is slowly ramping up over this 50-year simulation period. But as more and more pumping is applied to the model domain, our spring flow is going down and we're having extended periods of no flow.
When you're referring to spring flow, you're referring to the two you mentioned earlier.
Actually, this is just Jacob's well simulated, so this is just one of them. And then if you look volumetrically, that's 43% of total flow out of Jacob's well over that 50-year simulation. So yeah, overview, we have significant decreases in water level simulated from the pumping, and significantly low flow at Jacob's well spring. The other thing to point out is, if you look at this map, there's actually not a whole lot of predicted residual difference in water level here. And that's because of the hydraulics of this sort of the Blanco spring shed system. Sort of very low drops in water level can still result in significant impacts to spring flow. So it's an important thing to keep in mind.
When you say water level, are you talking about water level in the well or water level?
Water level in the aquifer.
Water level in the aquifer. Okay.
Water level in the aquifer. 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 Water le
Yeah, so typically, the way that we measure aquifer water levels is almost exclusively through wells.
The draw, that's where you measure the drawdown, wherever you think that the well is going to be on normal conditions. So at that level, that's the water level you're talking about.
Yeah, water level, or another name for it is hydraulic head, is kind of like the technical name for it, but it's basically, if you drill a well into the aquifer, if it's a confined aquifer, say the aquifer baseline is here, if it's a confined aquifer, the water level in that well will rise up to above the base, right? So that's what we're talking about.
Or that level, the water level that is in the well.
That is in the well, yeah. And over time, those water levels change.
Right.
Just through natural drought variability, or if you turn on a big pumping well right next door, that will also affect water levels. So what this model does is at a very coarse kind of regional scale, it makes predictive simulations about how those water levels will change.
Can I ask a question about the pumping files? Like your baseline pumping files, where does that information come from?
So it's a combination of all of our reported non-exempt pumping, which we got from Trinity, and we also got from our permittees. And then for exempt estimated, we have to just kind of make a ballpark estimate of what the amount of exempt pumping is. I pulled it from our annual report. So, you know, as part of the annual report, it always includes an estimate for the total amount of exempt wells within the district. And then we have the same for Barton Springs District. So if you go back to, you can actually see here, these same polygons is where I applied our baseline exempt pumping. So that's part of the baseline model. It includes.
So that's the exempt pumping?
Yeah, well, it's both. It's both.
Exempt and non-exempt? Okay.
Well, sorry, yeah.
Exempt and non-exempt?
So the non-exempt are not in the polygon. The non-exempt they have specific wells and they are located where they are in actual space.
I got you.
Sure. What are the sort of streamers that you have running through there that, I don't know how to define them other than the one to the left?
So
The little worm tubes.
those are actually water level contours. That's the potentiometric surface. So this is a screenshot from our actual modeling software.
No, I mean the
Worm
wider
tubes.
things that are purple.
Oh.
And
Purple
fluid.
and light blue.
Yeah. Those
Is that the bell comes?
those are faults. Yeah. So I wasn't planning to go into a lot of detail about the specific model construction, so I wasn't prepared with slides for that. But one of the another key conceptualization we made with the model is we've applied faults as barriers. So this purple, the purple is actually a module within ModFlow that's simulating a barrier here that's along that mapped fault. So that's what makes the computer simulation on this side, the water level will be higher and then it'll kind of drop off. And that's how we got the model to sort of line up with what the reality of what the data we're seeing is. So as you can see, I mean, there's an infinite amount of just little adjustments and tweaks that you can make with these models. You're always going to have to make simplifying assumptions, right? You're never going to get perfect calibration because of how complex these models are.
Could you repeat sorry,
Go ahead.
could you, on the slide you were on before, could you repeat the point you were making about Jacob's Well and that you don't see a lot of, no.
This one.
Yeah, you were making a point about not seeing a lot of residual drawdown.
Right.
What was your point there?
Just due to the nature of this part of the aquifer, where you have complex groundwater, surface water interactions, small amounts of drawdown here can still result in significant impacts to your spring flow.
But you're showing small amounts.
Yeah, you're showing.
You're
Correct.
Very small amounts.
Yeah. This line is the 1 foot contour here. So within this is less than 1 foot.
And you're attributing that to the surface water connection with the groundwater, another good recharge
It's
areas.
just a highly transmissive part of the aquifer.
Exactly. So one rule of thumb is like really high transmissivity areas. You can pump them a lot, but you're not going to see much change in water level. But vice versa, if you have a spring here, the spring kind of acts, it kind of naturally anchors that water level. So it's gonna be harder. You're not going to get that water level to budge much with all these springs.
So on that, the red is very low water and the green is higher.
The red is
Simply plug their own.
the red is the biggest difference, the biggest impact from pumping is the way to think that.
Oh, okay.
So we're taking our baseline and we're taking our pumping scenario and we subtract them. And that the higher numbers mean that the difference between the two models is biggest here, which means the model is simulating that higher levels of drawdown will happen due to that increased pumping within the confined zone than the unconfined zone.
So red are the highest impact,
Correct.
even though it's at the bottom of the chart.
Correct, yeah.
Okay, so, yeah, I was confused by the reversal of the red and green.
Linda Kay?
Yeah, so, the little red and yellow end that's up, is that Jacob's Well area?
This up here?
Uh-huh.
This is the Henley area.
Oh, okay.
And I would probably wouldn't read into this. This is kind of at the very boundary of our area of interest, so it's also an area that I haven't put as much effort into calibrating that portion of the model. So I wouldn't read too much into this little
Okay,
bullseye up here.
so Jacob's Well is down in the larger.
Yeah, this is Jacob's Well, this is Pleasant Valley Spring, and you can see
Okay,
Cypress
that's
Creek here.
my next question. Where is Pleasant Valley Spring?
It's this little guy right here.
Right there, okay.
Carlos?
In the model, do you also output the flow rates at the springs?
Yes. Yeah, I mean that's what this is.
Okay, so the level is low, but also what is important to point out is that the flow rate is also diminished.
I'm sorry, can you say that again?
The level that you show on the contour lines has increased, as indicated, but also the flow rate has increased.
Correct.
So it's important that people know that it's a double whammy in the sense that the water is not going to trickle as fast, even though the level is only one foot lower, you said?
Correct, yeah. And so more specifically, in that particular area where the springs happen, it doesn't take much of a drop in water level to make that spring flow go down.
So the left side of that chart is 2020, and the right side is 2070. So all that flatlining is going to start well before 2070.
So yes, for this particular modeling scenario. But you have to keep in mind that this assumes a dramatic increase in pumping over time, 2.6x.
Like Hayes County being the fastest growing county in the country.
Right. Yeah, this is basically assuming that there's not going to be any alternative water resources, and that all of that growth will be applied equally to groundwater as fast as population is growing.
Jeff, I'm also assuming you have constant climate throughout that entire 50 years?
So the climate it's a 13-year cycle. So our calibration period is 2008 to 2020, which it actually is a pretty good. It captures both a significant drought that happened from 2009 to 2015, and then a significant wet period from 2015 to 2020. So what we do is we take that 13 years and we just cycle it over and over until we get to the end of the 50 years. And both of these models have that same base
So
recharge.
they're really you're not looking at climate change from the past. You're looking at past climate, not future climate.
Correct. We have, so this, it's on the list of things to do is to apply climate change, but there's a little bit more complexity involved in that. So that's the wish list going forward. This is what we're able to do for now. I've got a couple of questions.
Thanks, Jeff. Welcome home. Good to have you back in the district. Excellent work, by the way.
Oh, thank you.
And we've got Rick over there who will report back to Al. He's always extremely impressed with your abilities. So thank you for all that you're going on to do. I've got a couple of simple questions. Have you done any water dating?
So any water what?
Dating. Have you dated the water in various elements of the region?
Oh, absolutely. Yeah, we have a pretty comprehensive. You talking about like isotopic dating?
Yes.
Yeah. So we through funding with the development board, both our district and Hayes Trinity gets allocated funding every year to do sampling, and part of that funding is age dating, sort of isotopic sampling. So that informs a lot of our understanding of the conceptual model, right?
Right. And so then without getting into great detail, what is the range? Because with that data, as you know, we have a better idea of when this water's entering and how long it takes before we actually get it out.
Right, yeah, I mean, yeah, for example, in our Blanco River area, you know, if you age the water there, it basically is like 99% modern carbon, right? So
Okay.
now I would be cautious about applying specific ages to water, because even with the isotopes, it's a pretty complex procedure to sort of accurately quantify what the age of the water is. But you can look at things like percent modern carbon or the presence of tritium, which is another thing that we sample for, because when we tested atomic bombs back in the 50s and 60s, it put a whole bunch of tritium into the atmosphere. So basically, if you find tritium in the groundwater, you know it's probably younger than 50 years, right? That tells you something. But again, it's harder to know, to apply an exact age to that. So it tells us whether or not there's water, and it's a good indicator that there's recharge available in that portion of the aquifer. You have to be cautious about getting too quantitative with the age of the water.
So what's the point then?
Well, it's still useful information.
So you sound like a politician. What are the age ranges that you're seeing on the Middle Trinity?
Oh, I mean, we haven't run the actual age range calculations, but if you just take the analysis at its face value, it'll say anywhere from like 1,000 to 3,000 years. But again, we know that that's not accurate.
Why?
You know.
Back to the first premise.
Well, because
How responsive it is.
it's complicated, but the specific isotopes you're testing for, you have to do a lot of processing to that geochemical data before you can sort of get it to accurately line up with the ages. So we use it more as like a qualitative guide rather than a quantitative. You know, there's not necessarily a whole lot of value in like tacking an age to every area of the there would be, but I don't think that would be it'd be possible to do that.
Same question. Is it in your budget or in your plan to test for per and polyfluoroalkyl substances?
I don't believe so.
Because I think that would be really good if both districts started to do this, because we need baseline data. One of the things we always claim, especially if we're going to go to court, we want to make a change. What's the baseline data? If you don't have any, then people can say, well, then you really know science. And so, as that's something that's very prevalent, growing in our society, having that baseline data is important. For the simple reason that they're not combined with the age of the water. One of the things that may well happen is that before we run out of water, the water that we have will be unpotable. Therefore, being able to identify the cleaner sources of water will become vitally important.
I mean,
if the water is 1,000 years old and PFAS was introduced 50 years ago, doesn't seem like it's a big deal.
Right, but we're claiming that we have a recharge factor in this region. And if we're not actually witnessing that recharge coming out of our wells, then where are we getting our water? And if we're taking...
It's more of a water pressure than an absolute...
Actually, you're right, hydraulic pressure underground. Nevertheless, when we start to bring water from deeper wells that is more potentially contaminated, then the need to change our method of treating that water will come along with it. At the moment, our wells by TCEQ are regulated under a certain set, and if it's coming out of a river or a lake, then it's completely different, far worse, because of all that's present in it. So we need to know where these changes are taking place.
Well, I don't disagree with any of that, but I think maybe we've gone a little far afield from our main topic of discussion now.
Right, I'm going to pull this in because this is the report that was was requested, et cetera, and we could talk all evening with all these what ifs and did you, whatever. But this is soon to be, this is still kind of a draft, we've got a few things to do. And, but we thank you very much for this, it gives us a lot to think about, and it does make these other questions pop up. But I'm sure that you would be open to discussing that another time and place.
Absolutely.
So thank you very much, Jeff.